I guess our mics won't work.
Good afternoon, everyone, and welcome to our 1:30 press conference. We are hearing all about space debris preventing the runaway Kessler Syndrome. This event will be recorded and posted to our YouTube channel later today, and for journalists, the recording, as well as slides and any other materials associated with the presentation, will be posted to the Press Information Exchange also later today. Reporters online, you can use the Q&A box to submit your questions, and we'll get to them later in the order in which they're received during the Q&A session. And with that, I'll just turn it on over to our panelists to introduce themselves.
We're not sure these mics are working. Sounds like they are. Okay, good. I'm Thomas Berger. I'm the director of the Space Weather Technology Research and Education Center at the University of Colorado in Boulder.
Okay. My name is Zagay Atalau. I'm a postdoctoral fellow from University of Michigan.
My name is David Malaspina. I'm an assistant professor at the University of Colorado Boulder.
I'm Dan Baker, director of the Laboratory for Atmospheric and Space Physics, University of Colorado Boulder.
Launch right in. Okay. Well, I'm going to introduce the topic to everyone. Let's see, advance the slides here. So we've been introduced. And I'm here to introduce the topic of space debris and also how space weather and the environment of space influences the debris environment in orbit. So first, some quick definitions. Orbital debris, what is it? Well, it's anything that's in orbit around the Earth, any human-made object, really, that is no longer serving a useful purpose. So we're not talking about the active satellites up there. We're talking about the dead satellites, the rocket bodies, the fairings, the wrenches, the gloves, and things like that that have been left up in orbit and are still orbiting in any condition. And then there's lots of ranges of orbits around the Earth, if you will, and we identify three here. And low Earth orbit is generally where most of the satellites and debris are, as I'll show. That's from about 200 to 2,000 kilometers above mean sea level. Then we have a big range called medium Earth orbit, starting above LEO and going out to the geosynchronous band, which is the third range there, which is also becoming highly populated because that's geosynchronous communications and imaging and weather satellites that orbit with a 24-hour period and therefore look at the same part of the Earth all the time. That's at about 36,000 kilometers out there, as we'll show. I'll also talk about the thermosphere. This is the region of the Earth's upper atmosphere above the stratosphere and mesosphere, which is actually extending into LEO. So LEO satellites and debris are actually flying through the Earth's atmosphere for the most part. And that changes with space weather. The size and the density, if you will, of the thermosphere is highly reactive to the inputs from the sun. And in space weather, of course, is these short-term changes driven by the sun, which can impact environmental conditions in space, not only the thermospheric density, but radiation and solar irradiance also change quite drastically with space weather. And then finally, in the title, we have the Kessler Syndrome. This is something named after Donald Kessler, a NASA scientist who was the first one to point out that if there were a debris population in space and it started colliding with itself, it could generate a chain reaction, unstoppable chain reaction of further collisions, ultimately resulting in a completely filled up space environment. So that's the Kessler Syndrome that we hope to prevent. Here again is looking at LEO. This is a really nice diagram because it's to scale. A lot of space things you see are never to scale. So that is a scale image of the Earth. You can see that the LEO environment is this very thin shell, only going up to about 2,000 kilometers. And then the MEO range, as I said, is very large. Sitting in about the middle of the MEO range is the GPS constellation we all rely on to get us from point A to point B now. And then the GEO band out at 36,000 kilometers. So that's an actual two-scale diagram. Most of the debris and a lot of the active satellites, as I mentioned, are in LEO. This is a blow-up of the distribution of debris in LEO as a function of altitude. And you can see there's a very large peak at around 800 kilometers. And the different colors here are different collisions that have historically created debris. So you see there's the Cosmos Iridium debris in the orange, the light orange there. The dark orange is the Fingyong 1C debris from the Chinese satellite that was destroyed. And you can see these satellites used to have a single orbit, but when they were destroyed or they broke apart, those debris spread throughout the orbit range. There's another little peak at around 400, and then you can see the International Space Station down there comfortably at about 300 kilometers in the lower tail of the debris, so they're in a fairly safe neighborhood, as we call it. But the 800-kilometer neighborhood is quite concerning. It's got most of the debris peaking there. This is a diagram from Kayhan Space showing now the number of conjunctions per day, actually for 72 hours. This is a 3-day plot. And what is a conjunction? A conjunction is when the Space Force, which is tracking the debris that they can track, which is everything above about 10 centimeters, comes close to another object, or particularly an operational satellite, they issue what's called a conjunction warning. And right now, as the plot, it's a little hard to see, but the peak of the plot is in altitude here, around 550 kilometers, where the Starlink constellation is currently orbiting about 6,000 active satellites. And they're now getting about 2,500 collision warnings every 3 days at that altitude. And then integrated over other altitudes, we're well above 3,000 collision warnings per 3 days. So 1,000 warnings per day is average. We're averaging in just the lower LEO register. So it's getting difficult for satellite operators to determine which of these warnings is important and which they have to pay attention to. And there's a good example of why this is happening here. This is the launches into LEO as a function of time, starting with the Sputnik launch in 1957. So in 1957, there was one object in orbit, and you can see over the last 4 years, there's been a huge increase in the number of launches into low Earth orbit. That's specifically, again, the SpaceX Starlink constellation, the internet constellation, which is causing a large increase in objects in orbit. We call this our orbital climate hockey stick plot because it has this sort of same alarming, dramatic increase that we see in the global temperature plots. And it has the same relevance towards looking at anthropogenic impact on the environment, right? So there's now approximately 7,700 active satellites in LEO. About 25,000 of these, both those satellites and pieces of debris are trackable because they're 10 centimeters or larger by radars, for instance. But there's well over 1 million pieces of debris estimated to be up there that are not trackable by radar. And so we'll have some speakers talk about how we can determine these distributions with more accuracy in the future. But right now, we're just estimating. There's a lot of things up there that we can't track, but something 10 centimeter in size would still destroy a satellite if it were a direct collision. So they're very dangerous objects, even though they're very small. And then I'll end with this one recent near-miss event, which would have been catastrophic had it actually occurred. At about 608 kilometers, I'm sorry, there was a NASA active satellite, the timed satellite, taking space weather observations of the mesosphere, so we use the data all the time, but it doesn't have propulsion on board, so it couldn't move when the Space Force told them, hey, you're gonna come very close to a dead Russian spy satellite, you should move. And they said, well, we can't. We didn't think back in the 90s when we designed the satellite we were gonna ever need to move. So that was they just had to sit and watch as these two objects approached. They didn't collide, which is the good news, but the near miss was 17 meters. So these things were estimated to come about 17 meters apart with a relative velocity of 14,000 meters per second. So that would have been a hypervelocity impact, creating thousands of pieces of debris at 600 kilometers. And that's happening more often, these near misses. One last point here, the reason there's these big sort of uncertainty bubbles and the reason it's an estimate of 17 meters is because we really don't know where things are in LEO orbit because they're moving around all the time due to the thermospheric expansion caused by space weather. So they'll ping it with radar, they'll locate it precisely with radar. By the time it's gone around one orbit, it's moved because it's got drag from the atmosphere moving the satellite to a different orbit. And so the trackers who are trying to keep track of all these collisions have to put these big uncertainty bubbles around them to say, we think it's somewhere in here, and therefore we think the probability of collision is X, but it has big error bars. So one of the things we need to do research-wise is to get much better at predicting thermospheric expansion as a function of solar input so that we can tell these operators, we can give the operators better certainty on the atmospheric density they're flying through, and therefore hopefully better accuracy on exactly where their satellite is at any given time. So I'll end there and pass it to Sige, who's going to talk about how we might see some of the smaller debris that we know is up there, but we currently can't track.
Okay, thank you so much. My name is Sige Atlau. I'm a postdoctoral fellow from University of Michigan, and I'll be talking about how we can use ground measurements to detect these small debris. So this is part of the Sintra project that's sponsored by IARPA, where our team is looking at detecting debris that are smaller than 10 centimeter using the signatures that are RF emissions due to collision of debris. So as I said, that we have over millions of debris that are smaller than 10 centimeter, which are currently non-trackable. So just to briefly explain about our methodology. So currently in orbits, there are collisions that happen that frequently and happening at higher speed, which could be anything between 10 kilometers per second to all the way to 70 kilometers per second if you are considering meteoroids collisions. So this type of collisions are known to create this high energy which evaporates and ionize the materials of the debris, which creates this ionized air or debris fragment. And this plasma starts expanding and emitting radio frequencies, which we think can be detectable from ground-based radio observatories. So to talk about the collision rates, there are about at least estimated that there are up to 1 collisions per second happening in range of altitudes if we are considering debris that are 10 micrometers and above. And because of this basis, we think that we can use debris collision signatures for identification of debris and tracking. So this method of detecting impacts or collision events is not new. Previous studies have shown that the impacts from meteors on lunar surface could be detected by using the radio observatories, for example, the Arecibo radio telescope, and was also confirmed using optical telescopes from ground detecting impacts from meteors, and they were able even to determine the size distribution of this meteor's impact. So radio measurement and optical measurement could be well used to determine this kind of size of different debris. So I'm not going more in detail, but so based on this analysis and understanding we have started looking into observations data. So this is the sample data from the Greenback radio telescope showing the signatures we are looking from the radio observatories. So there's no pointer here, right? Is there a pointer? Okay, so if you look closely on the spectrogram plot, we see a very narrow, sharp, wideband signal, which is observed at different frequencies. That is like in time scale of few microseconds. That is detected from the sample data set. So we have the numerical simulations that shows that if we are okay, this is what I was talking about. These are the type of signatures we're looking from the radio observation data. So based on the numerical simulations we have now, we say that if a millimeter size debris is colliding at 10 kilometers per second, we expect to see that power, emitted power, from all the way to 6,000 kilometers in altitude using the Greenback radio telescope working in this frequency band. So from this current analysis, like a sample of data set we have analyzed, we have identified multiple events such like that, but we are trying to pinpoint to what the source of these signatures are, because we expect it could be this kind of collisions between debris or other source of broadband signals like lightning or arcing also could be a signature. So we are, in the future, we want to utilize measurements from multi-instrument like optical measurement and RF measurement to pinpoint to these sources accurately, and also develop machine learning methods to accurately and efficiently identified these broadband signals for space debris identification and tracking. So based on our current understanding, we can we think that we can detect micrometer size debris all the way to a geosynchronous orbit. So yeah, that's where we are. Stay tuned for more results from our research. Thank you.
Hi, so again, my name is David Malaspina, assistant professor at University of Colorado, and I'll be talking again about the smallest debris and kind of why we want to track the smallest debris as opposed to looking for these sort of larger things that may eventually lead to collisions. The first thing I want to put up is this, just to point out on the top here, this is that very similar plot to what Tom showed, but this one's looking at sort of LEO and MEO and GEO, and what it's colored by are the relative risk of being hit by a human-made object versus a natural object. Space, of course, is full of natural meteors that are moving around all of the time. It's the leftovers from planetary formation, and spacecraft do get hit by those things all the time. But the risk in LEO and the lower MEO orbits is now completely dominated by human-made objects. So we have sort of filled that environment to a greater extent than nature has been able to. What I'm interested in are the smallest debris, so things that are like paint chips and fragments of thermal blankets and little bits left over from collisions. We're interested in a range from 1 micron up to 100 micron, which might be very fine sand, sort of all the way up to a few millimeter, so like a grain of rice. Now, those size particles are probably not large enough to destroy a spacecraft outright, but they can do some serious damage. If you have optics or careful certain coatings on your spacecraft, these can chip away at them, sort of like being sandblasted. You're also getting hit with a lot of them. You can also sever fine wires that may be carrying important signals across your spacecraft. So maybe the whole thing doesn't die, but suddenly you lose part of your spacecraft. The other really important reason to look at the smallest debris is this curve. This is showing you the flux, so basically how many things you're getting hit by per meter of spacecraft per unit time as a function of the debris size. And this is showing you all the different ways we have to measure these things. And when you get down to the largest objects, the flux is pretty low. So maybe 6,000 spacecraft or something spread over all of LEO space is really not that much in the grand scheme of things. But when you get down to these small particles, you're getting how many orders of magnitude? 1, 2, 3, 4, 5, 6, 7 orders of magnitude more particles, so 10 million times more small things than there are large things. So if this Kessler Syndrome starts to happen and we start to see a sort of cascade of collisions, we're going to see it in the smallest grains first. These are our canary in the coal mine. So that's really what we want to be tracking. However, our usual ways of tracking those small particles either don't exist anymore or have been retired. So what used to happen is the space shuttle windows and radiators were inspected by hand when this thing came back to the ground to look for little craters and count them up. We can't do that anymore. That asset has been retired. The smallest debris is not exactly observable by radar at this time, although there are exciting new techniques that may be able to do that soon. So what we have is this gap. We can't measure the smallest particles, which are the ones that tell us when that cascade is about to happen, or they'll be our first warning. And so what I've got up here is this sort of new generation of debris detection. I say in situ, that means detected by something in space. So one possible debris detection technology that we've been working on at CU is a combination of technologies that we use to detect the natural meteor environment. And sometimes we use them to detect dust particles, for example, at Saturn or at Europa. But here we're trying to taking those techniques, or close to the sun, we're taking those techniques and combining them into a sensor that we can use in low Earth orbit. There are other technologies where you spread out a beam of light and wait for things to pass through that beam of light and then count the particles that pass through. And then there's this idea that some of the smallest debris can create a wake behind it, much like a boat creates a wake through water, and that we may be able to detect that wake to tell when particles are getting very close and start counting them that way. So there's this whole new generation of in situ detectors targeting that region of debris that we have sort of lost visibility on. Right, so this is just an overview of what I just said. And really the takeaway here is that what we want to target, again, are the smallest particles that are going to tell us about whether that sort of cascade has begun and to what extent it will continue. Thank you.
Yeah, I'm Dan Baker. I want to talk more broadly about policy issues related to low Earth orbit. And how do we maintain, how do we assure a sustainable future in this crucial part of near-Earth space? As you've heard from previous panelists, the recent launch and operations of space-based systems has really caused an unprecedented shift in the way things are working. This rapid growth is driven primarily by communication satellites from the US that are being put in place. To correct one thing that I think Tom said, there are actually over 11,000 operational spacecraft in low Earth orbit. Next week, there may be 15,000. I mean, things are rapidly changing. The debris fields are increasing rapidly associated with this and other activities in low Earth orbit. And the effects on optical astronomy, on radio astronomy are really devastating. I'm sure many of you are familiar with a classic article that was published in the journal Science in 1968 by Garrett Hardin. It spoke about the tragedy of the commons. It was presented initially in sort of prosaic terms about grazing animals in a village pasture, but the implications were much more profound than that. Stated simply, the tragedy of the commons is that individuals acting rationally and individually, according to their own self-interest, will deplete a shared resource, even if this is contrary to the best interests of the group. And I believe that we are watching the tragedy of the commons play out in low Earth orbit right before our eyes. There are many things that need to be done to address this, but we have to have a greater regulatory framework, as this slide notes. There has to be governance. Some decisions have to be made and enforced. There has to be sustainability of satellite operations, and we have to control the effects on optical astronomy, nighttime astronomy. The leakage of signals from spacecraft is creating another kind of problem for radio astronomy. And the main theme of this press event is really the satellite collisions and orbital debris and things that need to be dealt with there. And there needs to be an international cooperation. This is not just a problem for the United States or for United States interests. It's really a worldwide problem. So there have to be steps taken to deal with these pressing concerns. And we have to define the current landscape. I would say that we know from meetings like the ones we're engaged in here at this AGU, that we as humans have polluted the oceans, we've fouled the atmosphere, we've desecrated the land masses in many places on our home planet. We must do everything now possible to avoid desecration of near-Earth space, which I believe is happening. And so a remarkable warrior and leader said long ago, we did not inherit the Earth from our ancestors, but we're borrowing it from our children. This was Lakota chieftain Crazy Horse. And I believe that there are many things that remain undone in low Earth orbit, and many things that are going to be greatly inhibited unless we deal with the debris issue, unless we find some way to control the proliferation of objects, man-made objects in low Earth space. But whether it's transportation getting to and through near Earth orbit, whether it's providing the very enticing, low-cost and widely available communication from low Earth orbit, platforms like the space station and other future devices like that will be impacted, or facilities that we haven't even dreamt of yet. And so I believe that we're all here to talk about some aspects, but there are manifestly more aspects that need addressing. And I would just like to conclude my remarks by saying that The United States, I think, needs to take leadership. I believe that Congress, the United States Congress, should really step up. And our delegation from Colorado has been leading some of the efforts here. Senator Hickenlooper and Congressman Neguse have been active in getting the Orbits Act. We can talk more about that. But we really need to have, of course, more research, and we need to take some concrete actions. And I think it begins at home, and I believe that we all have to play our role. And so there's information here about further information, and I think we all on the panel would be happy to answer any questions you have. Thank you very much for being here.
Thanks, Dan. And our other panelists will now open the Q&A session. Again, a reminder for the reporters who might be online, you can go ahead and use that Q&A box to submit your questions. And then for reporters in the room and online, please do provide your outlet when you ask a question, and we'll open the floor to any questions.
Yuichiro from Kyoto News, Japan, and thank you for your talk. And I have two questions. The first one is about the urgency of Kessler Syndrome. Is there any research to estimate the possibility of Kessler Syndrome happening by such as lab experiments or numerical simulations? That's the first question. And the second one is about the scalability of the observation of the tiny debris. How many ground stations or facilities are needed to cover the whole sky or whole Rio region? Thank you.
In terms of studies to simulate the Kessler syndrome or estimate when it might occur, I don't know of any explicit studies that came out with a definitive answer. One of the problems with that is, as mentioned, the probability of collision is very low for most of the calculated collision warnings, for instance, that are issued by the Space Force. I mentioned 1,000 a day in the lower registers of LEO, probably 5,000 per day total. Of those thousands, maybe a very small fraction are actually concerning collisions, and even smaller fraction occur, actually. And we haven't had a major collision since 2009, I believe. So we had a very close call, as I mentioned, but so it's a little hard to do a definitive calculation like that. Plus, the other wild card here is space weather, always changing the environment up there so that things are moving around. So it's an interesting misnomer to say something's in an orbit around the Earth. The orbits are always changing, and so it's a difficult calculation to make. I'm not aware of anything that's been definitive about, at this point it will get to a Kessler runaway syndrome.
I guess I might remark that right now there are 11,000 active satellites and all the other debris that's there. Present plans call for tens of thousands of more satellites to be launched into orbit. And as that population increases, the probability of collisions increases and the probability of Kessler syndrome goes up dramatically, in my opinion.
I think the other part I would add to that is it really depends what orbit you're in. So the higher you are, the further you are from the thermosphere, where drag might help pull you out of the orbit or circularize the orbit. The higher up you are, the longer debris will stay there. And so whatever gets added there tends to stay there, and the probability gets higher. So again, I'm not sure of definitive predictions, but I do know that the higher up you get in altitude, the more likely it is to happen.
Yeah, that's a good number to put in, that it takes centuries to come down from about 1,000 kilometers up. And if you're at 500, it's more like 25 to 50 years from atmospheric drag pulling you down, but it's centuries if you're at 800 to 1,000.
I see Mike Karlowitz here. We should pray for very intense space weather. I think that's what we need, is to clear low Earth orbit.
Second question was for you, as to how many dishes would you need to cover all of the sky?
Yeah, so if we're talking about how many dishes we need to cover the whole sky, there will be like so many of them. But technically, if we have good enough resolution from few telescopes, like we can use models to predict the other orbits, the orbital dynamics of this debris. So we are not looking into like covering the whole sky for now. Thank you.
Hi, everyone, and thank you all for the presentation. My name is Esma, and I'm from EGU, the European Geosciences Union. My question is more community-related. So how can community-driven initiatives, such as citizen science or educational programs, help mobilize public pressure to drive changes in regulations or on a policy level to address the risks of space debris? Thank you.
Yeah, this Dan speaking. I would say that it's really crucial to have more people speak up more forcefully. We've been very quiet as this what I call the tragedy of the commons has been developing, and I think we have to get a deeper understanding of what the impacts are. We have to understand what the mitigation techniques can be. One of the things we've proposed, and it's not the panacea, but it is a beginning, is to have an activity workshop undertaken by the national academies to get industry, government, academia together in the same room and talk about what can be done to minimize the effects, to minimize the consequences, and to understand what regulations can and should be put in place. And this, again, has to be done in a worldwide way. I think we cannot just assume that we in the United States can do whatever we want and then we'll put in regulations that will control the rest of the world. We really have to do this on behalf of all humanity. So that's rather platitudinous remarks, but I think it really is, we have to get serious about this and recognize that unless we do something, we are in imminent danger of making a whole part of our Earth environment unusable.
I'll just add that from a citizen science standpoint, a lot of amateur astronomers can see these constellations in Leo these days flying over as they're getting reflections off of the sun. They become visible in their long-term exposures, their long exposure images. And so amateur astronomers are very aware of this problem, and it could possibly help track the increases as they occur.
There was a study done by the Jason group that when fully deployed, the Starlink constellation, from any point on Earth, 5,000 spacecraft could be seen from any point on Earth, just in that visible region around that point on the Earth's surface. Imagine what that will do to amateur astronomy as well as professional astronomy.
Bas den Hond, freelance and for Trouw daily newspaper in the Netherlands. I'm still trying to get a picture of this Kessler Syndrome. If I understand from one remark made just now, it can happen at one altitude and not at another. And the second one is, if it happens, I'm assuming because some threshold density has been exceeded, how quickly would then that orbit or orbits be basically unusable? How fast would that go? And then what do we do?
Yeah, those are very good questions, and I don't know that I can answer the questions. I can clarify that it's not necessarily, it wouldn't be restricted to one orbit because as you saw when I showed the plot of where the debris currently is in Leo, those were all of those sort of distributions of debris were created at one orbit, one altitude, but they've since spread because of the atmospheric density drag spreading out the debris. So if the Kessler syndrome were to start at one orbit, it would eventually propagate to all orbits. How long that would take is the answer I don't know. And it's again, I don't know that anybody's done a simulation of an actual Kessler event taking off. And we just know from statistics that it would be an exponential increase with some rate of increase that I think is still TBD.
I think it would depend a lot on sort of the initial distribution when it started. So it probably will start at one orbit that exceeds that critical density and then spread. But the question is, what are the initial conditions at the other orbits? How far does it continue to spread? So I think there's a deep sort of orbital dynamics physics question there. And I don't think there's a straightforward answer, especially since the environment is changing so rapidly.
If I can follow up, this is so important and so catastrophic. And the question, what do we do? I've heard no answer. And yet no one has even done a ballpark calculation of how fast it would go and how long it would take. That's surprising to me.
Well, there are many ballpark calculations, but they're exactly that, ballpark, right? And so they vary by many orders of magnitude as to when it would begin, what the critical densities are. And again, the environment is constantly changing. So I think there have been many estimates, but there's no definitive number, if that makes sense.
If you want an extreme version, watch the movie Gravity. That is a preposterous exaggeration of the way things would work, but it gives you some idea of, on some time scale, how things will happen.
What's the range of the estimates?
0 to infinity.
The question is, what's the range of estimates?
Attending an orbital debris conference last year, the range of estimates that I saw presented at that conference were anything from tens of years to hundreds of years. So I don't know, right? That's a very broad range, and that was based on measurements of debris that were valid 2 years ago. The numbers are completely different now, so I don't know the latest. I imagine you have to continually update that model based on launches.
And as to the question of what can be done, one of the things that needs to be looked into is how do you remove the debris? I mean, there's a lot of active satellites up there, but there's much more debris than there are active satellites. And these are rocket bodies, as I mentioned, fairings, pieces of satellites, heat shields, things that have fallen off. So there's lots and lots of debris up there that far outnumber the active satellites. Somehow figuring out how to remove those debris would be of great utility.
Sorry to keep mentioning problems instead of solutions, but another concern is that some of the methods that are talked about for debris removal may create bigger problems by causing more collisions and causing more, a greater proliferation of things rather than a reduction. So as in climate mitigation, climate and geoengineering, I think one has to think very carefully about what one tries to do to solve the problem and not create a bigger problem in doing so.
And I think we have a question or two online.
Yes, this question is from Leo Enright at Irish TV. He says, for Dan Baker, the color-coded orbital debris density map seems counterintuitive in that much of the debris seems to migrate to higher parts of LEO. You would expect the debris to be migrating lower, so how do you explain the discrepancy?
I think that was my plot. And
I think it was yours, yeah.
Yeah, that is, those are created in collisions. And so during the initial collision, some debris was sprayed to higher altitudes. And as mentioned, the higher the altitude, the slower it comes down. So that the higher altitude debris is slowly coming down, but not nearly as quickly as the lower altitude debris, which is explaining most of the debris is in the lower altitude tail of those distributions. But the higher altitude tails are created in the initial collision which are typically very kinetic events. As CK showed, those clouds spread out rapidly, and in the cases of these large satellites colliding, they spread out to the order of 100 kilometers in altitude in some cases.
Okay, any other questions from journalists in the room? Yeah.
Hi, Kasha Patel, Washington Post. Can you go over a little bit more about the Orbits Act? You mentioned a little bit there, but you can go in more detail and describe what are things that are missing from it that you want it to be there?
So I don't quite follow the question. What is
about the
missing?
Orbits Act?
Oh, the Orbits Act.
Yeah.
Oh, okay, I'll leave that for Dan.
That's Dan all the way. So.
Yeah, and I'll also call on Heather Benet, who knows this intimately, but I think the Orbits Act is really intended to encourage the agencies NASA and other agencies to really support more actively the techniques for orbital debris removal and mitigation. And that was introduced by Senator Hickenlooper previous term and has now been signed on by Congressman Neguse in the House. And so this is not urging, but directing, I think, the agencies to get on with this and to do something about it rather than to talk about the problem. Is that essentially correct, Heather? Okay. Sorry for missing that, Tom.
We have a couple of online questions.
The first question is from freelancer Rick Lovett, and he asks, what type of methods have been proposed for removing debris?
There's a company in Japan called Astroscale, which is flying a mission to essentially either mechanically or magnetically, I can't remember, maybe both, grapple objects, approach. It's a small satellite that has propulsion and control such that it can closely approach other objects and then grapple the object and then deorbit both buses down into destruction in the upper atmosphere. I think there's been other experiments with, or at least designs with things like nets that go out to enshroud another satellite or piece of debris. I don't know that any of these have yet been proven to be successful. The problem is, of course, a lot of this debris is spinning and tumbling, and so a tumbling rocket body the size of a large school bus is something that you really have to wrap your head around to think, how am I going to first capture this and then drag it out of orbit? So it's a very difficult problem, but I don't think it's insurmountable given resources and engineering.
We have a few more online questions. This one is also from Leo Enright at Irish TV. He asks, is there a case for launching a long-duration exposure facility like the one that flew in the 1980s to do a long-term assay of these very small pieces of debris? Has such a mission been discussed? It might fit nicely into the cargo bay of a starship.
I mean, so these are things, so some of the concepts that we've shown earlier for small or smallest debris detection, from space, the ideal, of course, would be to get those things on orbit and to find some way to deploy them so we can monitor the situation. Right now, for the smallest particles, we're pretty much blind to them. And so finding either ground-based or space-based techniques or a combination of the two, I think, is really critical to doing that. Otherwise, we really can't see what's happening at the smallest scales, which is where each collision that happens, if you smash two large objects together, you're going to end up with mostly small objects as a result. And so if we see anything rapidly changing, it's going to be in the small objects first. So I don't know, I agree with you. There was the LDEF facility that was up for a long time. It was, of course, retired, and nothing has replaced it.
On the other hand, I think one could say that everything that flies in space, whether it wants to be or not, is a detection facility. And I think what needs to be done is to examine more things that have been flying in various altitudes. And I don't think there's any reason why that couldn't be done very efficiently and very effectively. LDEF flew for such a long time, it was really a question also of what was the frequency of interaction at different sizes.
And it flew in a very different debris environment than currently exists.
Yeah, right. And so I think that would be one of the simplest kind of experiments that could be carried out by the operational agencies, is just to fly some witness plates at various altitudes and just see what the problem is.
Yeah.
One additional online question.
Okay.
This is
No, I just want to add also, like, this capability of being able to detect debris collision actually will also help us to identify, also track very small debris that is created because of the initial debris. So this method, if we are able to detect debris collision, initial debris collision, then we can also track smaller debris fragments from the collision.
Okay, great. This question is from Mike Wall at space.com. If SpaceX does fully deploy its planned constellation of 42,000 Starlink satellites, how much would that increase the Kessler Syndrome risk? Have those calculations been done?
I'm not aware of any calculations, again, that are accurate or reliable at this point of a Kessler Syndrome onset or what the addition of more satellites would do. I mean, it's obviously going to increase the risk of it occurring, but how much is, I don't think it's been reliably quantified, at least to my knowledge.
That's right. One thing that I think is interesting is that the method by which various organizations put their satellites into orbit is also some question. I think Starlink, for example, launches to lower orbits. If their satellites are operating okay, then they boost them up to higher altitude. Launching more directly into these higher orbits just increases the probability of rocket bodies and other debris being emplaced directly in space. And so I think there are also strategies, tactics that could dramatically change how big a problem is created as we add tens of thousands of more spacecraft to low Earth orbit.
Okay, any other questions in the room? We're at time, so. Okay, well, with that, thank you to our panelists. I don't know whether to feel optimistic or just scared, but it was interesting either way. Our next press event this afternoon is at 3:30. We have a media roundtable looking at how cities are adapting to climate change and how science is helping them do that. Yeah, thank you all.